Hello and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. For today's episode, I am joined by Tudor Williams, who is the CTO of a company called Filtronic. And the reason that we agreed to do this podcast was because I was very, very interested in GaN technology. And that's something that Tudor and Filtronic are working in and exploring how it can be applied in various applications, from electric vehicles to autonomous technology and radar systems and all sorts of exciting stuff. And Tudor very kindly agreed to come on and share his knowledge with me. So welcome to the show, Tudor.
That's right.
And I wonder if we could just get started with a bit of background about yourself.
Yep. So I've been involved in RF engineering for quite some time, actually, so about 20 years, and did a PhD at Cardiff University. And I did a bit of design work working on some MMIC design, so semiconductor design, including some GaN work actually at that point as well. And I worked for a startup for a number of years. Quite an interesting journey from a startup. Lots of hard work and lots of travel. We were selling measurement systems for semiconductor test. Again, linked into our semiconductor piece. Then after that, I went to the Compound Semiconductor Applications Catapult. So it's a government-run institution looking to grow that market in the UK. So I headed up the RF team and then became Director of Technology at the Catapult as well. And then finally moved about 3 years ago to Filtronic. Filtronic specialised in RF systems, right through from design through to manufacture in their headquarters in North East England.
Some people might have picked it up already, but you have a slight Welsh accent.
I do indeed.
There's a bit of a semiconductor cluster in Wales, and you mentioned the Compound Semiconductor Catapult, which is also located in Wales. Can you tell us a little bit more about sort of what led you into the semiconductor industry and electronics industry in general in the first place? Was it seeing all of that around you, or what kind of inspired you?
I guess that probably wasn't really a thing when I did my PhD.
Yeah.
And ironically, my PhD was almost by accident into RF. I was actually planning to come and do a PhD in power electronics. So again, linked to semiconductors, but my PhD supervisor at the time pulled out at the very last minute, about 2 days before he was due to start at Cardiff University, and I got transferred into RF, having never done it in my life. So kind of a curveball that probably served me quite well. It's in the end. I think I've done some interesting stuff since then. Yeah, a bit of a curveball.
It's often the way, actually. Like a lot of the guests that we have on the podcast, they took up their particular field. I mean, power electronics is another one. I mean, that kind of wasn't really a thing. I mean, not that I'm saying you're old or anything, because you're really not, and I'm the similar age, But back when we were thinking about studying power electronics was sort of very different to what it is now. Motor design, I think, was the less interesting part of the electrical engineering course in a lot of cases. But these things have really come on vogue, and RF in particular, obviously, is very much the world runs on wireless systems these days. So when something feels like it's the right time to be doing it, it's probably a little bit too late.
I think that's true, yeah. You see that all the time, don't you? People jumping into a field where it's suddenly on vogue when it's probably too late, as you say. It's full already, So yeah, we've got lucky with that one, I think.
So you mentioned in some of your experience history there, a really interesting term, which I came to know, but for the benefit of the listeners, you said MMIC. So could you just explain what that acronym means?
Monolithic microwave integrated circuit. It's basically an entire circuit on a semiconductor chip, basically. Typically in some sort of compound semiconductor material or silicon. But yeah, so a MMIC. It's a very small, couple of millimeters across, and that would have all the functionality of an amplifier or maybe even a subsystem. So transmit receive chip, for example.
Yeah, and so these are chips, and they're chips that are getting designed and developed and sometimes manufactured in the UK, certainly in Europe, for use in mobile phone systems and radar systems and sort of other applications.
Yeah, that's right. So yeah, we don't have much manufacturing in the UK actually for RF anymore. We got a small boutique fab called Inex in the northeast, and I think that's probably the only commercial RF fab left in the UK. Europe has a couple, as you said, in France, so UMS and Mecom now own a fab in France too.
So if I kind of swing back, we'll get on to Filtronic in a minute, but I just wanted to open up GaN. So I mentioned GaN at the beginning, and some people listening might not have heard of that term before. So in power electronics and in electronics in general, we've got different kinds of switching device technology. And compound semiconductors obviously is a big field that's really sort of emerged in the last few years. Some people will be very familiar with silicon carbide switching devices. So that's been kind of the mainstay really of the transition to more kind of high efficiency, high performance electric vehicle powertrains, all based on silicon carbide switching technology. And this new technology, GaN, I say new, it's not particularly that new, but it's not necessarily widely commercialized yet, is a gallium nitride switching devices. I think I've got that right, gallium nitride.
Yep.
What's that all about? Can you sort of tell us a bit more about GaN and why that's important?
So this was my background's RF, as you know, Ryan. So I have a little bit of a slant that way for GaN. It's been, I guess, adopted a lot faster in RF than it has in power electronics. And so took a long time though. It was 20 years ago when it first got established. And like all device technologies, really, it takes quite a long time for them to mature into material processes, and also for the cost to come down. So they typically start on smaller wafer sizes and then get scaled to larger wafer sizes, brings the cost down, and then that's an entry point for more industries. And it typically starts with defense, because defense have the money and they'll pay for performance. So that's what we saw in GaN. It was heavily invested in the US in particular by the DoD in the US, and they developed devices that had better performance. And so GaN's a wide bandgap material, so really high voltage operation. It leads to higher efficiencies in RF as well, and higher power densities. So you can do the same application, same power levels in a much smaller chip. So you really drive down the size of the device, but also increase the efficiency, and has a number of other benefits in the RF domain. It's got lower output capacitance, for example. So you can match it much easier with a wider bandwidth. If you're trying to do a really wide band design with high efficiency, GaN's a really good option for that as well.
So it's all about getting faster switching devices that are lower switching losses and more efficiency.
That's it. So more efficiency is the key, really. It's driving up that efficiency point. And the world of power electronics has efficiencies that are very high compared to RF anyway. So the RF efficiencies are much lower. So they'll typically be looking at, if you're in the sort of 20, 30 gigahertz range, you're talking about 30 to 40% efficiency. So quite low efficiencies, and the areas where Filtronic work, much higher millimeter wave frequencies at E-band, so 71 to 86 gigahertz, you're talking about efficiencies at about 10%. So you're talking really low efficiencies where you have problems related to that then with thermals as well. Obviously, you're dissipating a lot of heat in a very small die area. You have to remove that heat. So a lot of the engineering is in the actual mechanical and process engineering, and to actually manufacture parts.
And this, I mean, that sort of thing about efficiency really starts to add up. I mean, obviously, if it's a few isolated defense projects, with special purpose radar systems or something, then maybe it wouldn't be so much of a concern. Although the on aircraft power consumption or on system power consumption is a thing in that space. But then a lot of the wider applications where GaN is being used and the sort of RF systems are coming into play, where actually there's an awful lot of kit in the world that's sitting there doing various RF jobs, consuming power. So huge power consumption in things like mobile phone systems, for example.
It's massive. I think that mobile phone energy consumption in the base station in particular, where you've got high power amplifiers transmitting to your mobile phone, it is massive, and it's one of the bigger energy consumptions in the world. Again, when they talk about airline traffic, I think it's very similar to sort of airline consumption of in terms of carbon footprint. So it is massive, and not just an environmental impact. Obviously, it's a financial impact for the mobile operators. So they can save a couple of percent in efficiency, that's dramatic for them. That's millions of pounds they can save electricity cost.
And in a lot of cases, I mean, mobile phone base stations is a really good example. You've got to locate them. Sometimes you have power available and sometimes you don't. Actually, it's quite a common thing around the world for mobile phone base stations to be kind of off-grid and powered by other means. So savings in efficiency actually can be huge cost savings in operation for that sort of infrastructure.
Yep. Yeah, I think what you talked about, the in-car piece as well. If we start to get to autonomous vehicles, obviously, again, power consumption becomes really important. We're all moving towards electric vehicles as well, so they'll have limited battery capacity. Anything that is going to steal a lot of power from that battery and reduce the range is going to be critical. So they're going to want these things to be as efficient as possible when you get to that domain as well.
And does it even apply to sort of handheld devices as well? Like power consumption actually?
It's critical, isn't it? I mean, your battery life on your mobile phone, for example, is driven by the efficiency of the PA, power amplifier in your phone. So range of power amplifiers actually because of different bands. They're the biggest consumer of energy in your mobile phone, and improving that efficiency has really driven the lifetime of the batteries and the fact that you can now run a phone for a couple of days, if you're careful of it. So that's really been a big drive again for the handset market.
And are we finding GaN devices now in sort of consumer products like mobile phones, or is it still limited to base stations and infrastructure?
It's mainly in the base station market just because of the higher power levels required. So gallium arsenide is still sufficient. I think in mobile phones in general, you tend to see gallium arsenide still used widely in PA.
Cool. Okay, gallium arsenide. So that's a different compound semiconductor, and that's probably a neat segue into Filtronic and some more about what Filtronic does. So you mentioned. Filtronic's a company close to me in that, as many people know, I'm located in the northeast of England, so a bit of a northeast business. It's not a new company by any stretch, and it's got a really interesting history, but absolutely knocking it out of the park at the moment. Must be the new CTO that's made all the difference.
Actually, that's not the case, but yeah, we've had a very successful 12 months. Buoyed by some new business actually in a new market for us in space. So yeah, we go back 40 years. We span out of Leeds University 40 years ago, and the focus, given you can probably tell by the name, was filters. So it was a filter company originally. So our filters mainly for defence applications, but grew quite rapidly actually, and grew to a very large size. I think it had a market cap over £1 billion at one point. So we had 2,000 employees. Comms boom, so we were involved in the handset market actually. So we were making switches and devices. We had our own fab, our own gallium arsenide fab at one point as well in Newton Aycliffe. But since we've divested lots of our business, we had the boom and bust of that dot-com era, and frankly, it just became too expensive to manufacture in the UK. It's such a cost-driven market. All that business now belongs in Asia. It's in Taiwan, it's in China. Where the cost of the production is much lower. So that kind of all disappeared, and we reformed the business focused on defence and comms, sort of really specialising in a certain part of the comms network, the backhaul. So most of what we do these days is all about moving large amounts of data from one place to another. So really high bandwidth, high data rate comms links. So that's the backhaul. More recently, then we've pivoted into space. And we've seen a real big shift into that. When I started 3 years ago, we had no business in space at all. It's now the biggest market we have in the business. So it's been transformational really for Filtronic.
And most people, like a lot of times we think about the space industry. I mean, not that many people think about the space industry because it is, away from us by nature, can't see it. But people who might think about it might kind of think, it's a pretty small industry in terms of satellite launches and expensive sort of low volume stuff. What is it about the space industry now that's sort of driving that activity for you?
So I think the space market's gone through a massive transformation in the last even sort of 5 years. We've gone from an industry where you have very expensive, massive satellites in geo orbit, which take 10 years to make, and they last for 40 years in the sky. So big companies involved in that, people like Thales Alenia Space and Airbus, and that's really a specialism is that space sort of project. But obviously we've had an influx of LEO space, so low Earth orbit. satellites. So these are much smaller satellites, and many more of them. They have constellations of satellites to get worldwide coverage. And the most famous one is obviously SpaceX and Starlink, and they already have thousands of satellites in orbit. And what that's done is really flipped space into its head, and rather than having everything done to perfection and at very high cost, they said we now need things that last only a short amount of time, so maybe 5 to 7 years in the sky, and we want the cost to be much lower because we're going to make thousands of these things. So the cost point has to be much lower to make the business case for that comms broadband piece that they've got. So it's really flipped it on its head, and that's really where companies like Filtronic have suddenly become interesting. They're saying you're doing stuff on the ground on the comms side at really high frequency, it's E-band link, high data link. Could you do that for space? And we saw a first sort of influx of that into what's called the HAPS market. So people like HAPS, so it's high altitude pseudo satellites. So they're things like they can be fixed wing platforms, or they could be balloons. And one of the most famous ones, I guess, was Google Loon. They had a balloon-based system. And we actually partnered with Google on that project as well. So we did the first demonstrator with Google and had a world record data link from air to ground, 40 gigabit per second data link, which is quite impressive. It's a lot of data being moved from one place to another. So we did that with Google. That was a sort of first sort of departure into space about 6 or 7 years ago. And then since then, I've been working closely with others. And most recently announced a big strategic partnership with SpaceX back in April, I think, this year. So that was a big play for Filtronic.
And are you allowed to say sort of specifically what is it that you do for them?
Yep. So we've been working with SpaceX on the ground segment. So we're supplying at the moment power amplifiers, so very high power at very high frequency. So it was that 71 to 86 gigahertz again. So it's the uplink from the ground. So that's 81 to 86 gigahertz, so very high frequency. And we're delivering about 20 watts of output power at that very high frequency, which is state of the art. Nobody else in the world has that sort of capability. And we're supplying those parts into SpaceX's network and manufacturing in volume for them.
And what kind of technologies are involved in that sort of thing? I mean, presumably these things are MMICs that you were talking about before.
Yeah, so because of the high power levels required and high frequency, we actually have to do lots of combining as well. So we have to combine many MMICs into a single output port. Parts that we're shipping at 81 to 86 gigahertz at the moment have 32 individual MMICs, which are all designed in-house at Filtronic. We design our own MMICs, and we do the full integration. So we do everything from chip design right through to the manufacture of the modules. And that's all done again in Net Park in the Northeast. So they're at the moment on gallium arsenide, and that's because of the very high frequency range. So 81 to 86 gigahertz until very recently wasn't within the range of gallium nitride. So we have to work on a slightly lower power gallium arsenide chip set to get that performance. We're now starting to work on an E-band version in GaN as well. So we're starting to see, the last sort of 12 months, we've seen a couple of fabs in the world. So people like Northrop Grumman and MMIC in Europe, actually, in the US and Europe, with much lower node sizes, 90 nanometer nodes for GaN. And that's really pushing the frequencies up to that sort of 100 gigahertz level where we can start to see that GaN being used for higher power. And it's really transformational in terms of power output. So you go from producing maybe 1 watt in a gallium arsenide MMIC to maybe 3 or 4 watts, or maybe even 5 watts in a GaN MMIC. So you get that much higher power operation in the same chipset.
You mentioned a really interesting thing there, which again, we're going to do a lot of this, I think. Just unpack a little bit for me what you mean by node size.
So the node size is the gate length of the transistor. So you see this in every technology from silicon right through the common semiconductors. And obviously in silicon, the node sizes are tiny. They got really small node sizes in silicon, which means you get very high performance operation. And it's in silicon, I guess, to do with transistor density. They get billions of transistors onto a chip. It's a little bit different in RF. We have a few transistors on a typical MMIC. But again, the node size in RF really drives the frequency of operation as well. So the lower the node length, the shorter the gate length, effectively, faster the transistor can operate. So you get higher frequency operations, higher FTs. That means we can use them at high frequency and get the amplification that we want at much higher frequency.
Right. And it's that is that kind of node size basically if we're thinking like conventional silicon device, that's sort of the Moore's law thing of, getting faster and cheaper all the time.
That's it. Yeah. So pushing that performance. As I say, typically in common semiconductor, we have much larger node sizes, than compared to silicon. That's just because of the equipment we use for that.
And is it the sort of manufacturing processes and the technology, or is it because you're actually switching currents rather than just logic?
Yes, it's quite a different process, I think, compared to a silicon process. I'm no expert in silicon, but it's a very different type of transistor, I think, and then the technology changes. So yeah, they're pushing, as I say, billions of transistors into a single chip. We're looking for power and power handling of chips as well as speed of operation frequency.
Yeah. And so this sort of backhaul type componentry, that's you got the uplink to the SpaceX systems from the ground stations up into the space. Is that? I mean, like, are there a lot of them? I don't know. It's a sort of I know nothing about that system. What does a Starlink system look like?
So I don't have all the details around, because obviously they don't share all the details with anyone, because they're quite secretive. But they do have many ground stations actually. So I'm not sure of the exact ratio to try and meet their demand. So they're obviously driving quite a lot of demand through that system. I think what they're finding is that the more users they have, the more users they get on board, the more data they need. So they need more ground stations to fill that data link back to ground. And they have grand plans, I think, at SpaceX to take a massive share of the broadband market away from the terrestrial broadband into space. So they're trying to drive that business case by just pushing massive amounts of volume through that system.
Yeah. Yeah, interesting. I saw actually just yesterday, I'm not sure if it was like a jokey kind of post or a serious one, but someone was talking about a mobile phone, equipped with Starlink system, and that could be a sort of big thing in the future. I don't know if the sort of I don't know how real that was or not, but sort of shows the level of ambition. And we're starting to see more and more. I mean, I think first house that I saw with a Starlink system a couple of weeks ago in fairly rural Northumberland, which I guess is a good use case for it. Farnborough Air Show last week, there was a couple of people with sort of integrated systems for mounting on smaller aircraft where you could, provide that sort of system. So there's actually a lot of applications for that kind of connectivity. If the cost could come down, it potentially could take out some of the fixed infrastructure broadband applications as well.
Yeah, I think it will becomes a cost piece, doesn't it? I think, as you say, the first adopters are probably going to be people who don't have connectivity or have poor connectivity, because that's a massive use case for this. And I think in the US in particular, there's big swathes of the US where there's pretty poor connectivity. It's a big country, so it's pretty hard to get the infrastructure in place, and it's costly, in a lot of areas. And we see that even in the UK, as I said, in the Highlands and other areas in the UK where it's quite expensive to put fibre in. So having a satellite-based system is useful. I think as we start to see the costs come down, and then SpaceX have transformed launch as well. Their launch cost is dropping all the time. They have their own launch system. So that cost is dramatically reduced for them. Satellites are getting cheaper. I think if they can get that business case going, it'll start to probably disrupt that market potentially. That's certainly their aim. That means it puts us under price pressure as well. So the suppliers are always under the thumb. It's a bit like the mobile comms industry. The price point is critical, getting that business case right.
And I mean, the mobile comms piece, so applications like 5G have really driven a lot of development in switching devices and the RF world. What's the sort of intersection between the 5G device that we have in our hand and this sort of backhaul technology like you've been doing for SpaceX?
So there's lots to talk about, full integration of 5G into space, non-terrestrial networks. I think, again, mainly the backhaul data at the moment, so where we don't have base stations, we can use satellite to backhaul data and make sure you get served everywhere. As you said before, there's a lot of talk about direct to cell as well from satellite, and there's lots of people interested in it. I think the first instance it'll probably be sort of SMS emergency type response type stuff, and I think that's already happening. I think Apple already have that integrated in their phone. I think Starlink are looking at that as well. But there are space companies out there who plan to put base stations in space effectively, so they replace maybe 1,000 base stations that are on the ground with a big base station in the sky and save it that way. So I'm always a bit dubious about these things, but then quite often I get proved wrong. So I've sat on many calls with customers thinking these guys are crazy, and then you go 5 years down the line and they're set up and running. So, never say never on this stuff, I think. And again, you talked about autonomous vehicles. That connectivity piece is going to be critical for that touch of technology to work. I think it needs to have constant, ubiquitous coverage worldwide, and I think probably the only way to do it really is to have satellite coverage. That's the only way I can think of it. Putting the infrastructure on the ground to cover the entire world it's going to be very tricky, I think. I don't know about you. I can't even get a signal in my house at the moment. So now I get no signal even where I am. So
yeah. Funnily, in my house in the northeast, it's not bad. Where I really struggle, which is always surprising, is down in Oxfordshire, which is I spend quite a bit of time down there, and yeah, like you'd think you'd have brilliant phone signal, but it's appalling across most of Oxfordshire, which does seem quite surprising. But yeah, so I mean, autonomous vehicles. Obviously, that's a big topic area of this podcast. Usually, autonomous and electric vehicles, and we're seeing a lot of developments there. And you mentioned the connectivity element, and a lot of people actually talk about this ACE, autonomous connected electric vehicles and transportation, and that sort of trinity of technologies coming together to make more autonomous vehicles a reality is quite an interesting one. I think there's different opinions in terms of how quickly autonomous vehicles are going to be seen, on the streets at scale. Obviously, there's vehicles out there today doing trials and demonstrations, and they've got a combination of sensing systems which have some overlap with GaN technology and the kind of work that you do. But then, when will that become more widespread? There's also, being at Farnborough last week, some interesting examples there where actually they're looking at effectively electric aircraft that are easier to fly because they are partially autonomous, so not necessarily fully autonomous, but making aircraft more accessible by making them easier to fly through the use of more autonomous systems, which is an interesting thing, because I don't know about you, but a lot of respect for airplane pilots and particularly helicopter pilots. Like, have to be able to do about 7 things at once.
Indeed. Yeah, absolutely.
Very difficult thing to do. So those technologies all converging, and the kind of things that we have where there is a sort of step across. So typically for an autonomous vehicle, you need to know where you are. So that'll be a combination. That's that sort of situational awareness of where you are and what's happening around you. Normally involves LiDAR, which is a laser scanning, radar, and actually radar is an application where GaN devices are being increasingly used, particularly in the aerospace and defense side of things for higher performing radar systems. You've then got vision systems as well, so there's interesting optical sensors and stuff going on, and GPS or GNAS, like various sort of. So you've got like on vehicle stuff, you've got reliance on satellites. It's quite a lot going on there.
It's a complex piece, and I think that's back to your point about when it happened. Again, it comes down to the business case, isn't it? And cost, I think, more than anything else. To be widely deployed, it has to come down to a price point that makes sense for the consumer. Nobody can afford to spend £200,000 on a car. So you've got to get that price point down, I think, to a sensible level. As I say, there's quite a lot of RF play in that system, and radar is something we work in as well. So we in the defence sector actually, but as you say, for defence aircraft, we're working on that sort of thing with some of the UK primes and manufacturing radar modules for fighter jets and the like. As you say, the GaN stuff has really come on there in the defence market in the last couple of years. They were originally gallium arsenide again, and they pushed into GaN for that higher power density. Again, it's around efficiency, not just in terms of power, because they do have power on the aircraft, but it's in terms of size. They're getting that low swap. They go to a swap size rate and power, and really pushing down the size of these things. They want to get more and more sensors on there onto the aircraft. They want to make them small and light. And that'll be similar for electric cars, again, for the same reasons. They want to light the cars, they want lower power operation. And then you can also get better range from GaN as well, so you can get much better visibility at a wider area, so you can get more power and you can get a bigger field of vision effectively from the radar.
Yeah, well, and one of the sort of things, although it seems trivial, but if you've any kind of autonomous cars that are out there at the moment, always kind of look a bit weird. um,
They do, yeah. They have these big domes on top, don't they, of the lidar, and
yeah,
yeah,
so sensors all over the place that can't be. I mean, even driver assistance systems which have radar in today, like forward-facing radar in a car, integrating that radar into the front of the vehicle is a sort of stylist's nightmare, trying to make a sort of big black blob look attractive. And in some cases they've done it well, or well-ish, and in other cases they really, really haven't. BMW, I'm looking at you.
yeah. I think there's always a compromise, isn't there, between performance and style as well. They have to make it work in both regards, don't they? You have to get the right performance from that sensor, but as they also try and make it look stylish and pretty. So it's smaller you can make stuff. Obviously, that really helps, doesn't it? If you can make something smaller and lighter, get the efficiency up. You need less thermal management, so you can get things smaller and tighter, much more integrated, and get the cost down. So you can get the cost of these things driving down.
And do you think, so for radar systems for autonomous cars, for example, do you think that GaN could potentially be a solution there, or do you see it being mostly for the higher performance radars for the kind of aerospace systems?
Again, I'm no expert in this, Ryan, but I think at the moment most of it's silicon. That's driven by cost, and the application is slightly different. Say it's a forward-facing radar. It doesn't have to do very much. It's sending something in front of it. But, obviously an autonomous vehicle needs to know a lot more than that. It's a much more complicated system, and he wants to know everything about what's around it. And I think there's always some trade-off between can we replace the lidar, with more complex radars then, that can get a bigger field of vision, more power, maybe high frequencies to get better resolution. So could we drive the cost down by going RF only? Lidars are very expensive and appear to be staying that way for some time.
And hard to integrate physically.
Hard to integrate physically as well. So yeah, so I think if we see that happen, you may well see that sort of move to higher technology node then to get better performance, more information, and then better data processing on board to get that system working properly.
I guess it's probably a similar argument in the more kind of commercial aerospace field as well, in terms of.
Yeah, absolutely. I mean, it's all about the information you need, isn't it? It's you pick a system for the complexity you need to get the cost down. So if you need something very simple, you use silicon, and you just do something very simple. If you need something more complicated, fighter jets and commercial aircraft, that would be definitely want more information and a better quality system. They're more likely to use the higher performance semiconductors, and they can bear the cost. They're not massively expensive these days. The cost comes down continually as they start to develop stuff. The cost has come down dramatically the last 5 years of Gallium Nitride, for example. Probably 2 or 3 times cheaper than it was 5 years ago. So it's just sort of pushed to bigger wafers, and maybe some compromise. So most RF devices are made on silicon carbide substrate. So it's gallium nitride on a silicon carbide substrate. But we're seeing GaN on silicon become more prevalent as well. So it's slightly lower performance because silicon isn't as good thermally. It does get a little bit hotter, but obviously they can scale at a much higher wafer sizes. So you can get much bigger wafers, get the cost down. And then obviously sort of a medium sort of application then could have GaN on silicon. If you're looking for very high-end performance, you go GaN on silicon carbide. So you've got that sort of compromise. And there's even talk then of, if you have GaN on silicon, could you start to combine the RF power piece with more logic and digital? Because obviously you have CMOS in silicon. Could you actually combine the two? And there's been lots of talk about that in the last 10 years, but that's being worked on with universities at the moment. So that sort of integration.
Bigger sort of system on a chip kind of.
System on a chip, so you integrate all the digital piece with the RF on the same substrate.
And probably touching now a little bit on, I know the first word you're going to say, but bearing in mind that, you originally were going to do a PhD in it, looking at the power electronics field and, so for power electronics, we're typically thinking about traction inverters for electric vehicles and power converters like DC-DC converters, or components used in charging systems or grid infrastructure and what have you. What's going on there with the GaN technology, and how come the comms space has really embraced GaN and kind of gone much more quickly with it? Why are we not seeing GaN more widely used in the power field?
it's a good question, man. I'm probably not the best person in the world to answer it, but from my understanding, it seems to be the GaN has been adopted in power electronics for lower power applications. I'm not sure whether that's because of the breakdown voltage or whatever, that maybe silicon carbide is slightly higher breakdown voltage. Maybe one reason. But I think I've seen obviously GaN being used in sort of laptop type applications and chargers for that, or power supplies for that. So I think it does have benefits then in terms of efficiency though. I think it is slightly better in terms of efficiency. I guess it's always going to be some combination of cost and performance.
Do you think we'll start to see more GaN in power?
I think if we see the cost come down, I think it will be adopted more. I think that there's always going to be that combination of cost and performance to say. And even if something's better, sometimes it doesn't get adopted immediately. We saw that in the comms industry too. We had much better efficiency than gallium nitride for a long time before it started to get adopted in comms because the price point was too high. It needs to make a business case. You need that combination of performance but cost, and cost drive down, and that sort of comes with adoption. It's a chicken and egg, isn't it? Really, someone has to start using it.
Yeah.
To get the volumes up, the volumes get up, and then the price comes down, and then more volume comes on board. So I guess that's the piece maybe power electronics are grappling with at the moment. Can they get the cost of that down to see that performance benefit? Gallium nitride.
Oh, interesting. It's going to be interesting kind of following that. I know there was last couple of years there was some sort of promising looking statements around some big car manufacturers booking capacity for GaN devices for various applications, and there've been some projects looking at improving performance in drive systems with GaN, and I think there's some things coming out there. But yeah, there's a lot going on at the moment. I think it feels like after sort of maybe 10 years where we've had a kind of bit of a steady state of particularly silicon carbide being adopted and scaled up and commercialized, that now actually that kind of era, there's a lot of change about to come.
So we see this in all industries. It's very similar, isn't it? That, technologies get adopted as they become commercially viable. As I say, it's a research thing at first, isn't it? You see the performance benefits, and you can show performance benefits, which is great. People have to be willing to pay for that as well. And you get early adopters, and maybe for power, it'll be things like space as well, where GaN is quite attractive for space applications. Again, it's got really good efficiency. It's radiation tolerant. We see that in DC power supplies for space starting to turn to GaN already, where the price point is affordable. So space are willing to pay a little bit more for the performance because it's really important. The power consumption on a satellite is critical. It's very expensive to put power into space, and obviously they have limited power supplies. They've got solar power maybe on satellite. They've got very limited ways of making power, so it's really critical. So efficiency is critical. Every percentage point they can save is massive. And again, we'll see defense adopt in the same way because they care so much about performance. And then when we start to see these early adopters, benefits come, and then they start to scale a little bit of volume, and then that'll seed larger volume into commercial space. And I think, again, automotive is quite cost sensitive. It's going to have to get the price point right, I think, to get the adoption. It may not be enough just to say I can get an extra 20 miles range on a GaN converter. It's going to cost another £10,000 for the car. I mean, people are not necessarily going to pay what they need to. Always a technology and commercial use case, isn't it, that we have to balance and get right.
Yeah, and actually, a lot of times I think scientists and engineers are guilty of forgetting that as well. That sort of commercial angle and the quality. Has it got the right price point? Is it going to last? It's because that could be another thing of. I know it is a bit of an issue with some power devices in GaN of actually proving that they're going to last. Just how do you validate that this thing is going to be good still in 10 years' time? That kind of question is really important. So for Filtronic then, obviously you're in your role as CTO, you're looking at the technology for today and the things that you're going to be doing tomorrow. What are the kind of areas that you're really focusing on with your research and the business sort of activity as you're moving forwards?
So I guess we've seen, I'd say, space has become a really important market to us. That's become our biggest market, and really rapidly. And we're seeing that grow continually, not just with SpaceX, but with other companies as well. And we're starting to look at the payload side as well. So I talked about ground systems for SpaceX, but We're starting to look at payloads as well. We won a significant ESA project last year, a £5 million project to develop payload hardware. You have the other end of that link, basically. So you got the uplink from the ground and then the
You could
downlink
see
back to the
the
satellite.
look. I mean, the listeners to the podcast luckily can't see the video, but you could see my face. They're like, "What does he mean payload?" That's another. Just tell us what you mean by payload.
Right, so payload is the satellite end. So the bit that sits on the satellite, so we call that a payload. So that's what sits on the satellite and does all the communication back to ground. So we're working on it again on that transceiver side. So the transmit and receive from the satellite side. We do the transmit side on the ground. We're looking at the payload end, satellite end, and which again is interesting. It's a slightly higher value, higher margin business because it's quite complicated to make. It has a lot more challenges with regards to, as I say, low size, weight, and power. High efficiency is really important. Thermal management is more tricky in the payload as well because you're in a vacuum. Moving heat around on a satellite is quite difficult. And also it needs to be radiation tolerant and fully tested. You need to guarantee the operation for at least 7 years. There's a lot of testing involved in product development. Of course, you're very rigorous testing in terms of radiation hardness, but also shock and vibration, thermal management, all that sort of stuff. Lots of testing, quite expensive testing. Costs upwards of £1 million to test a single product for space, so it gets quite expensive. So space is big, really interesting there. Filtronic, that's obviously going to grow. So that space piece is really important. The comms piece, the backhaul piece, we've seen probably slightly softer rollout to 5G than we expected. Everyone expected. I think it's hit everybody if you look at the market.
Yeah.
I think that's really because people aren't willing to pay for it again. You've got this business case piece. And I know if I've got a good 4G signal, I can do everything on my phone I need to do. So why would I pay extra to have 5G? So there has to be that business case from the end user as well to say I'm willing to pay for it because someone has to pay for it. It's going to be us in the end. They don't put the infrastructure in until someone pays for it. We've seen quite a soft rollout so far of 5G. I guess it'll be driven by applications. We'll see something new come out on the phone, some novel application with AI or some power hungry thing that needs lots of data, and that'll drive the market again. It'll reestablish. So we're still in that market and still interested. We still have roadmaps to high frequency, and even as high as D band. Quite a big shift in terms of the way you manufacture things as well. It'll do complete change for that. The high frequency operation.
Well, and what are those challenges? As you're pushing the frequencies, what does that mean from a sort of device perspective, technology perspective?
So it's really that integration piece. It's the packaging and how you integrate into a module as well is really important. Obviously, the higher frequency goes, the more loss there is. You start to chuck away power very quickly if you're not careful. But even traditional sort of interconnect technology from chip to the rest of the circuit becomes really important at that high frequency. So a wire bond we use at E-band is fine at E-band, and you can control that. You have very tight tolerance on that wire bond. But 170 gigahertz, you can't make it work. You'd need to correct every single circuit and adjust because of the parasitics change in the wire bond. You need to do something completely different. Flip chip is talked about. You may have waveguide interconnects or some new technology required, I think, to deal with that higher frequency operation, particularly for power applications where we have high powers and high power amplifiers. So we're looking in that area. We've done some early work on interconnects and how we might physically make that. And at the moment, we're at the point where you can make maybe one or two of them. So you can hand build 170 gigahertz, but we need volume. So when we were running our E-band transceivers, we could make maybe 3,000 a week. So we can make lots of these things. So you need to be able to do it very quickly and repeatedly. So you need to get that, not just the ability to do it, but the ability to do it at volume and mass manufacture.
Yeah.
So that's really the challenge then on that. So it's early stages on that, I think, at the moment. And even the semiconductor technology isn't really there at the moment. You can't get the power at 170 gigahertz that you can get down at the lower bands. So again, you're waiting for that technology to be developed. And then as soon as it's there, you need to be ready to integrate it, which is why we're doing all the packaging and interconnect stuff now. As soon as we have those viable devices in semiconductor, we can integrate them and get that product to market.
Oh, wow. Really ahead of the curve. Will that be GaN technology again, do you think, at those higher frequencies, or something completely different?
Possible at the moment. The only way to get power is indium phosphide. So another combo semiconductor. Yeah. Indium and phosphide. So again, at the moment, they can get about half a watt of output power per MMIC at 170 gigahertz. So that's the leading edge technology. At the moment, it's really expensive. So it's boutique fabs.
Yeah.
Quite small wafer sizes again. Back to that same old story. You have to wait for technology to become cheap enough to actually start to integrate it into products. Initially, at the moment, it's very high-end systems for defense again that use that technology for high frequency and high frequency sensing.
I was going to ask where else is. I'm not indium phosphide as. You've got to be good at your sort of names, haven't you, with the
You've got to
compounds?
be good at your chemistry. Yeah, you just have to reel off all the different combinations you can have.
Where else is indium phosphide used? But you've sort of answered that question before I've asked it. Any other applications for indium phosphide?
It's very good for what they call low noise amplifiers. So that's on the receive side. So, a lot of our focus is on the transmit side, but yeah, equally important is the receive side and trying to get the noise figure, they call it, down as low as possible. That gives the signal to noise ratio basically. So there's two sides of a link. You've got lots of power and you've got the receive side, and you can work on both ends of the link to try and improve that performance. If you take a dB off the noise figure, you need a dB less power just on the transmit. So it's really important on both ends. And indium phosphide again is another really good material for low noise amplifiers, and we use that in our links as well on the receive side.
Oh wow! So, obviously, you probably can't say all that much, but I'm going to ask anyway. What's the sort of next sort of year or two, the sort of big things that are coming that you're really excited about?
So really pushing forward with the space piece. So we've got a very crowded roadmap for space, which I've been developing since I started. So we've got lots of things on there. I'm really trying to disrupt that market. At the moment, the ground segment is all driven by what they call traveling wave tubes, so vacuum devices. They're very complex, very hard to make, and we're trying to disrupt that market at the moment with the solid state semiconductor technology. So we're leading the charge on that really, and I guess just trying to drive the whole product piece as well. So at the moment we make modules, and then maybe look at maybe making more of a product. So mains powered, fully tested, rack mounted amplifiers for ground systems is somewhere we're looking at maybe pulling the focus away to that as well, grabbing more of the system architecture. And in general, maybe that's a piece we look at as well. So we work in defense, we work in comms. Can we take a little bit more of the system? That's a good way to go to market. So rather than looking for new markets, take a bit more of the system. So looking beyond RF potential as well in the digital domain. There's lots of digital SDRs, so software-defined radios in use now. So trying to look at that and maybe leveraging some exciting applications in that domain.
Right. And it's sort of like an operational level within the business. Do you had a fab in the past? Is that something you think you'll end up going back to, or is that kind of
I think it's unlikely. I think I think probably one of the biggest and easiest ways to lose money is to buy a fab. And then I think we got bitten by it last time. That was one of the things that drove that massive divestment in the company. It's very hard to be competitive in semiconductors in the UK.
Yeah.
Not to say that someone can't do it. I think I'm quite passionate about it. I think we need that capability in the UK as well. I think we need it for power electronics. I think we need it for RF as well. I think particularly for defense applications, it's a very unstable geopolitical environment, and relying on Taiwan for your chips at the moment is making some people very nervous. So we don't really want to be doing that. But even within Europe, you want to try and get as much onshore as you can, if you possibly can. And I think the government's investing in that. They put a plan together, £1 billion investment over 10 years. So they're starting to wake up, I think, to the fact that these devices are critical in everyday applications. It's everything from your mobile phone right through to fighter jets and everything else. Critically important supply chain. I think COVID again taught us all a lesson about supply chains.
Yeah.
And that disruption in supply chain was massive, for everybody, including us. It caused us real problems with delivering parts.
Took the chip crisis to maybe switch a few more people on.
Yeah, I think maybe that's one of the best. There's always positives that come out of everything, and maybe one of the positives that came out of COVID. There weren't many, I know, but I think people did wake up and say, "Oh, actually, we better think very carefully about our supply chain. Can we get more localized supply chains?" And that helps everything, from information flow. I think is better when you have local suppliers. But even environmentally, rather than shipping stuff halfway across the world, if we can get things more local, it's a positive across the board, really.
Yeah, and obviously, just from a technology and sort of product standpoint, even without the fab, that would benefit Filtronic, or is benefiting Filtronic as you work more closely with.
Absolutely, and that supply chain has become more local, and we do a lot of work with local suppliers, even in the northeast, PCB manufacturers and metalwork manufacturers, and they're all local to us. And we have a very strong partnership because of that. And it may be slightly cheaper sometimes to do things in China, but it's not always better. Sometimes if you need very high quality, high tolerance parts, you need to work very closely with that supplier, and the big Chinese operations or Asian operations are not really interested in the sort of volumes we have, So what we think is high volume is tiny to them, and they're not going to work very closely with us. So finding a partner where we're important to them is critical. So smaller companies, I think, have to do that to get the best quality and the really good relationship and information flow.
Yeah. And one sort of final thought, obviously you're in a position now as a business where you're scaling again, you're growing the business, you're hiring people, looks like some really exciting opportunities in the business. How do you see the sort of skills piece panning out for you?
And I think the skills piece has been difficult as long as I can ever remember, particularly in these niche fields like power electronics and like RF. We don't have enough engineers basically in the UK. I think we need to work on that from an early level. So the STEM piece is really important. We're trying to start doing that sort of activity as well, working with schools, engaging young people to get into the business. But yeah, it's been a challenge. It's always difficult to find engineers, good quality engineers. So Filtronics dealt with that by opening new offices as well. So we've got our main site up in Sedgefield. We opened a new office in Manchester, and that's starting to grow now. It went from 3 people 3 years ago. It's now at 17 people. So that's grown pretty quickly. And maybe that's part of the answer, is to try and distribute ourselves a bit more around the UK so we can attract the best people as well. So yeah, it's a dynamic situation, but we need more people. We need more people now. So if there's any aspiring RF engineers around the UK listening to this, then please get in touch. Got some really interesting stuff happening at Filtronic. Yeah, we're always looking for good people.
Brilliant. And I think on that, it's been a really interesting discussion, Tudor. Thank you so much for taking the time out to talk to me and the podcast today. I wish you all the best in the future. Thank you very much.
Thanks very much. Thanks, Ryan. Really good to talk to you.